Imagine you're a really hungry university student, and you see that your university is offering lots of free food events today, each of which only being open for a limited amount of time. The time frame of each of these events is just the length of that line, and for the sake of simplicity, we'll also assume that you have to stay for the entire duration of any event you attend. Your goal is to get as much free food as possible, and we can frame this as an optimization problem where you want to attend the maximum number of events you can. We can call this maximum number of events opt, meaning the optimal or best solution. Now, from looking at this list, you might see that picking food 1 and food 4 would give you the optimal solution of 2 events attended, since the timings don't overlap, and that means that opt is 2. And there are actually a few different ways you can get this result. But how can we make a reliable algorithm for this? Well, let's just try a very simple strategy and see how it does. So we're repeatedly selecting the event that finishes first while not including any overlapping events in our solution. So as you can see, we first pick food 1 since it finishes first and avoid any overlapping events, and finally pick food 4, which is the optimal solution we had before. And this is called a greedy algorithm. You can think of it as always taking the best option each step. And in this problem, it actually always returns the optimal solution. But let's look at an example where this isn't the case. In this problem, we want to maximize the total value of items in a knapsack without going over the weight capacity. Each item has an associated weight and value, and our greedy algorithm chooses the next item by the largest V over W ratio. We start by choosing item 2 since it has the largest ratio, but we can't choose item 3 since it would make us go over the weight limit, so instead our only option is item 1. And this gets us a total value of 5 for the greedy solution. The optimal solution, however, gets a value of 6 by picking item 1 and 3, so we know that the greedy strategy doesn't always get an optimal result in this problem. So now we know that the greedy strategy is optimal with some problems, but not with others. So how can we prove this? Well, let's have a look at matroids. So a matroid is a pair of 2 sets, E and I, where E is the set of all possible solutions and I contains all the independent subsets of E. And this pair satisfies 2 properties. Set independence is hereditary, and this scary line, which essentially means the difference between a set from I and any larger set from I will also be an I. And this is used in the Rado-Edmonds theorem, which states that if the set of possible solutions form a matroid structure, then the greedy algorithm must find an optimal solution. Now, let's try a quick example to prove that greedy is optimal for the problem we saw earlier. Just to remind you, our greedy strategy always picks the event with the earliest finish time as long as it doesn't overlap with previously picked events. So our greedy algorithm picks the first and fourth events. Now, to prove that this is optimal, we introduce an exchange argument and ask, could a solution with a size more than 2 exist? And if that's the case, then an extra event in B can't overlap with the last pick. But this would mean that greedy missed an event, which never happens, so this is a contradiction, which means that our greedy algorithm does in fact get the optimal solution. And this is actually the reasoning that the Rado-Edmonds theorem formalizes for matroid structures. And just before we end off, it's important to note that there are actually optimal greedy algorithms that can have different structures, and you're free to research more into this if you'd like. Anyway, I hope you enjoyed learning more about greedy algorithms, and maybe you'll even apply some of what you've learned when analyzing or creating your own algorithms. And this is my first time making a video like this, so thank you for watching, and let me know if you'd like to see more of this type of content in the future.